Welcome, I'm Carl Tate. How many earthquakes occur each year for a given magnitude? Our topic today is the frequency of earthquakes. But to get into the frequency of earthquakes, we need to understand something about magnitude. The size of an earthquake can be described by its magnitude or by its moment. MW is the moment magnitude, M0 is the scalar seismic moment. The moment magnitude scale was established in 1977 by Hiro Kanamori, and it replaced the 1935 Richter scale. Earthquake magnitudes are determined from the analysis of recorded seismograms, and we won't cover this aspect here. So the moment magnitude MW can be determined from the scalar seismic moment M0, which is in units of Newton meters or joules for energy, using the following equation. So given M0, we take log base 10 of that number, multiply by 2/3 and subtract 6. We can go the other way as well. If we have the magnitude, we can take 1.5 times the magnitude plus 9. 10 to that power gives us the moment. So we can get M0 for every MW in a given earthquake catalog, sum up the total seismic moment for the entire catalog, and then determine what fraction of the total moment is accounted for with the largest events. We'll see these pie charts later, and that's the basic idea. Turns out there are many more smaller earthquakes each year than larger earthquakes. This fact was documented in 1944 by Bino Gutenberg and Charles Richter in a paper entitled Frequency of Earthquakes in California. From their paper, they found that the number of earthquakes for a given magnitude, here 6.5, it's relatively small, and as you go down to smaller magnitudes like 3.5, where there were more than 579 earthquakes. And they found that this relationship could be expressed as a line where the log of the total number of events had a intercept term and slope term, which we'll explore next. So here's the expression. This is the Gutenberg-Richter frequency magnitude relation. And it shows n is the number of earthquakes having magnitudes larger than magnitude m. B is the slope of the line and determines the relative proportion of larger events to smaller events. The way it's written with the negative sign, B is always positive. And A is the y-intercept of the line and determines the total number of events. So this simple relationship, which expresses that there are many more smaller earthquakes than larger ones, can be visualized in many different ways, and one of which is shown here. So from this USGS chart shown here at the right, there's magnitude going up on the y-axis. There's the energy release, equivalent kilograms of explosive shown for each of those magnitudes. And this curve here is showing the number of events, number of earthquakes per year, 1 million magnitude 2s, 100,000 magnitude 3s. And the main point is that there's fewer earthquakes of the largest magnitude per year. On the left is another version of this plot, just a little fancier, kind of highlighting some of the recent earthquakes and exploring facts about, magnitude, for example, doesn't determine the number of fatalities or the damage. There are other factors that go into the significance of earthquakes, but the main plot here is showing that there are many more smaller earthquakes per year than there are larger ones. Let's take a look at some catalogs of earthquakes. And for our purposes, we need to know only the origin time, when an earthquake happened, and the magnitude for each earthquake. From that information, we can say surprisingly a lot about the occurrence of earthquakes. We'll look at two catalogs. The first is the GCMT, Global CMT Earthquake Catalog. This is a snapshot from the webpage showing the occurrence of these earthquakes in the catalog 1976 to 2005 here. We'll be looking through 2022. From that same webpage, there's a figure that's generated showing the cumulative moment or energy of all earthquakes starting from 1976, the start of the catalog. And by design, the curve is always increasing to the right. Each time there's a new event, you add in the moment and this curve gets higher and higher. So from any earthquake catalog, we can also construct this kind of curve ourselves. There's thousands of events in here, and the biggest steps in the cumulative moment represent the largest events. So the stars here are the earthquakes greater than magnitude 8. So here's what this looks like if we take the catalog, the GCMT catalog 1976 to 2022. And what we find here is this is the occurrence of the largest 20 events in the catalog. We see them, not surprisingly, around subduction zones, sort of the ring of fire in the Pacific. The largest 20 events are all magnitude greater than or equal to 8.2, and we can see them. They're also plotted here on the left. And so we have this cumulative events where the biggest steps are happening associated with the largest events. 2004, Sumatra, 2010, South America, 2011, Tohoku, magnitude 9.1. These big steps are where the biggest events are happening. Other periods of times, things are pretty steady. From 1976 to about 1995 or so, very steady, and not any of these largest events happening. So this is the cumulative moment since 1976 for the GCMT catalog. And that shows there are 59,681 events. And the total, if we sum up all of the moment and convert back to magnitude, would be a 9.63 earthquake during this time period. Just to highlight, one of these events is from Alaska, the Chignik earthquake, July 29th, 2021. And on the units at the left, a very small step, still a magnitude 8.2. That's the event right here. We can also make a pie chart showing the fraction of the total moment within each of these events. So here's the largest 20 events, each one from the largest event going to smaller events, going around in that direction. So we have the largest event, 9.1, Tohoku, Japan earthquake in 2011. The next one in the catalog was the Sumatra earthquake, and these show the top 20 events, all the stars shown at left. As we go down to the smaller events, we see here in the less than magnitude 6, there's 54,000 events. They don't make up a very big slice of the pie. And that's one of the points of this discussion, is that there are many smaller events, but they don't make up a large amount of the moment of the energy released by earthquakes. So since 1976, the largest earthquake, 9.1, was much more energetic than the 54,159 earthquakes in this catalog smaller than magnitude 6. It's kind of remarkable to think about that of all the energy released, it's really tied up in these biggest ones. The smallest ones do not produce a lot. On to the next catalog. We want to go further back in time before 1976 to look at a longer record of earthquakes. This is the ISC GEM catalog screenshot from that webpage. And so for our analysis, we're going to combine the ISC GEM catalog 1904 to 1976 and the GCMT catalog for 1976 to 2022. So our previous plot from 1976 to 2022 can be seen kind of up here, compressed, this toward the end. And now we're going to add in back to 1904 to see a much bigger picture, a longer record of earthquakes. And here's a new set of 20 events. Now the top 20 events are larger. These are 8.4 and larger. And so we can see, again, they're in pretty similar place around the ring of fire, mostly associated with subduction. So here's our plot. And we'll highlight a couple things. The largest event was in 1960 in southern Chile here. And we see it was 2.7 times 10 to the 23rd Newton meters. This is 2.7 is the step taken from about here, 3.2 to 5.9. So this big step right here is given by 2.7 times 10 to the 23rd. You see the 10 to the 23rd up here. And that represents a 9.6 earthquake, the largest ever recorded. So that gives an idea of kind of these big vertical steps represent the magnitudes for the moment. We also have the sort of big five Aleutian earthquakes. So on this top 20 list of events of all time, there are five in the Aleutian Alaska subduction zone, which we'll discuss in a different Alaska earthquake science fact. And here's the pie chart for this total catalog. Now there are 75,964 events. The total magnitude of everything in the entire catalog is actually 9.97. If we look at the pie chart to break down the moment, we have the Chile event, 1990, 9.6. We have 1964 Alaska event shown here. It's a 9.3. Tohoku, 2011, 9.1. So these are the top 20 events that make up over half of all the energy is just in the top 20 events. This is the magnitude 8 to 8.4, 7 to 8, 6 to 7, and this little slice of 63,000 or so events are everything less than a magnitude 6. So we can look again, since 1904, the largest earthquake, 1960 magnitude 9.6, was much more energetic than all 63,776 earthquakes smaller than magnitude 6. Pretty impressive, gives you some appreciation for just how big these large earthquakes are in terms of the energy released. And even more, this one event was more energetic than all 74,000 earthquakes smaller than magnitude 7, this wedge here, and comparable to all 76,000 events smaller than magnitude 8. Over this 120 years or so, one event is comparable to the energy released by all earthquakes smaller than magnitude 8. And 8 is a really large earthquake. So just to break that down, kind of our picture, we have one event, magnitude 9.6 in this pie chart, 91 events in the sort of 8 to 9.6 range, and another sort of quarter here in the magnitude less than 8. It's really intriguing to think about cutting up this energy release pie into these sections to see really how impressive these largest events are. So the Gutenberg-Richter frequency relation is basically taking earthquakes in each magnitude, counting them, and plotting them. So this is another picture of the catalog we've been looking at. There's 75,964 events represented here. Magnitude is on the x-axis, and the number of earthquakes is on the y-axis, with the important point that they're scaled logarithmically. So we have 1, 10, 100, 1,000. And that's because the relationship by Gutenberg-Richter assumes that you've scaled the magnitudes by log base 10. So what you do here is you take your catalog, count the number of events in each magnitude bin. For example, 172 events between magnitudes 7.2 and 7.3, and then plot this blue triangle. And you do that for each set of events in your catalog to get this picture. The red squares represent the cumulative number of events toward the smaller magnitude. So there are 809 events with magnitude greater than or equal to 7.2. So this represents sort of the sum of all these blue triangles to the right are represented by this value right here. And it turns out this cumulative curve turns out to be a little smoother by this. And the drop off at lower magnitudes shown here, and on the cumulative scale, it just flattens off because you're not adding any more to the left here. But this drop off in magnitudes is because smaller events are harder to detect since the signals are smaller. They don't appear on some of the seismograms. So this drop off determines what's called the magnitude of completeness for an earthquake catalog. So for this catalog, it appears to be complete down to events that are about maybe 5.5. It's subtle to decide where that is, but the point is this drop off is saying that we don't have the instrumentation to detect all these tiny events that are probably happening all the time. So from this, distribution, you can see that they kind of follow a line, and this line, this data can be fit using a procedure to find a best fitting line. And so that's shown by fitting this red line. The cumulative and incremental distributions have the same slope, but they have a different y-intercept. They would go through magnitude 0 at a different height, but their slopes of these two lines are the same. And this is what the A and the B value of the Gutenberg-Richter frequency magnitude relation is about, saying we're going to represent this earthquake catalog with a line. And as it turns out, this global catalog seems to be best fit by two line segments rather than one. You can see that when we put in, here's one line, and here's another line with the sort of steeper slope, and they kind of cross over right here. These are not critical details for the sake of understanding what we're trying to show here, but just saying that you could see that two line segments would fit this data better here. And so here's our picture of the real data. This is the global earthquake catalog, 76,000 events. Here's the pie chart that we saw. And we can also use this A and B value to consider what a idealized earthquake catalog would look like. What is the implication for a small number of smaller magnitude events based on this relationship determined from these larger magnitude events? And so here's what the idealized distribution would look like. As it says here, the idealized catalog has the same A and B value as a real earthquake catalog. So if we go back and forth, we can see that the lines are the same. It's just that this is idealized, that they have sort of exactly the same expected number of magnitudes in each bin. And you can also see that the pie chart changes a little bit as well, but it's kind of similar. So these catalogs would be expected to have similar magnitudes of events, ideally, or real data at the higher magnitudes, but then at smaller magnitudes, the idealized data says there's much more. We're saying here's an idealized catalog where we can detect even all the small events. And in this case, less than magnitude 6, there's some 300,000 events. So that's what we expect is actually happening on the Earth. We just can't pick up all these events with the distribution of stations that we have globally. But we have very good reason to believe that there truly are thousands and millions of small earthquakes happening. So here's a comparison between the actual data and these idealized data. And on the right, the only thing we used to make this pie chart in this catalog were the A and the B value determined from the real data. So from this B value and A value, we can generate a set of catalog and make this pie chart that should have kind of similar properties to the real data, in the sense that here's one event representing, a quarter of the total moment. Over here, it's a 9.7 that represents more. For the magnitude 8 and up to that size, there's about roughly half or so, and about a quarter for the magnitude less than 8. But the point on the right is that the Gutenberg frequency magnitude relation gives us an A and a B value. And from those alone, we can get a sense of what we would expect the breakdown of energy for the catalog to be. And in this case, it's just telling us that most of the energy released is in the largest events. Earthquakes less than magnitude 8, it's roughly a quarter of the total energy release is happening in these smaller events. And yet they represent the vast majority of the number of events in the catalog. So the main points: the Earth produces far more smaller earthquakes than larger ones. The cumulative energy of earthquakes is dominated by the largest ones, even though there are very few of them. These points can be seen from the USGS plot, though it takes a bit of effort since you need to multiply the number of events multiplied by the energy release per event. But we can see there are far fewer events up here, and many more of these smaller events down here. Or you can see it from this fancier version of that same plot. Or you can see it from the pie chart that represents the total energy in all the earthquakes. This is the 76,000 events. And we see that the number of events shown here of the smallest events, 63,000, 11,000 magnitude sixes. As you go toward the larger magnitudes, there are very few events. And yet, when you sum up all the energy from those large sets of events, they make up a tiny wedge here. And it's actually dominated by the largest events. These top 20 events taking up over half of the energy release since 1904 on the planet. And another way to show this is the Gutenberg-Richter frequency magnitude plot, just another way to show this information, where we have the number of earthquakes at largest magnitudes is much smaller in the sort of 1 to 10 range, whereas as we go to the smaller magnitudes, and this is in log scale, there are thousands of events at smaller magnitudes. But better than all of this is the equation that provides us with this best fitting line, which is log base 10 of the number of earthquakes can be expressed in terms of an intercept value and a slope term, the B value, that determines this sort of occurrence of number of small earthquakes relative to large earthquakes. So all we really need are A and B, these two numbers, to explain and characterize the frequency of earthquakes on the planet Earth or in a given region, wherever you are. This seems to be a universal empirical relation, a property of earthquake occurrence. And from these A and B values, we can even make practical statements about how often we expect earthquakes to occur. This may be the kind of numbers that people are looking for. And so from the A and B values that we derived from the catalog of 76,000 earthquakes, these are the kinds of statements that can be made about the recurrence interval or the number of earthquakes per year within a particular magnitude range. So for example, magnitude 5 to magnitude 6 earthquakes, we expect one on the planet every 201 minutes, so about every 3 hours. And that amounts to about seven magnitude 5 to 6 earthquakes per day. Or we can say a magnitude 3 earthquake happens every minute, or 2,060 per day. These statements are directly derived from just the A and B value and the Gutenberg-Richter relation. Or a magnitude 8 earthquake every other year. So the recurrence is about 2 years. Or a magnitude 9 every 30 years. So the takeaway topics: the size of an earthquake is quantified by its magnitude, MW, or its moment, M naught. Magnitude can be calculated from moment and vice versa. There's no upper limit or lower limit to the magnitude scale. Negative magnitudes are permissible, and so are magnitudes above 10. The Gutenberg-Richter frequency magnitude relation is a line represented by a slope, a B value, and an intercept, an A value. The Gutenberg-Richter frequency magnitude relation describes how there are many more smaller earthquakes than larger earthquakes. Although there are many more smaller earthquakes, the collective magnitude of these smaller earthquakes is much less than the collective magnitude of the fewer larger earthquakes. Global energy radiated by earthquakes is dominated by the largest events. In the endnotes here, this just shows some details about where these numbers come from, such as the 6.0674 and also the 9.1010 that appeared earlier. As before, the scalar seismic moment M naught here is in units of Newton meters, which is joules, energy. And these are just some notes to show from the original equation in their paper, it can be rewritten in a more familiar way by combining a couple terms. Interestingly, the B value they listed for the California earthquakes of 0.88 is within the range of what is found globally, between basically 0.5 and 1.5. Wherever you are, this relation seems to be hold, and it's pretty close to 1.